Alright, just a quick recap of some of the stuff that we were talking about in class recently. So we talked about charge interactions, so we know that we have positive charges and negative charges. We know that they are governed by the law of romantic comedy, which I really should trademark it some days, which tells us that opposites, such as a positive and a negative, are going to attract, and that like charges, such as a positive and another positive, are going to repel. These would attract as well. Anyway. We then took this idea and put it to the idea of, some materials. We said that we had things that were conductors and things that were insulators, and that conductors were things like metals and people and water that hasn't been deionized, and that insulators were things like rubber, plastic, usually stone, I would say, is probably a good insulator. And that in conductors, these charges that we have, they're free to move. And in insulators, charges are less free to move. And so kind of the interesting idea about this is that if we have a conducting blob, then we think of this as being just kind of a sea of positive and negative charges. Because all of these charges are free to move in here. And because, as we're going to get into later on, all of matter is made up of atoms, and atoms are made up of charged pieces. So that means that this whole thing... Oh, I should have counted this before I started. That point is another minus there. Minus there. Alright. And so, all of this is made up of matter. Matter is made up of atoms. Atoms are made up of charged particles, protons and electrons, specifically. And protons are made up of quarks and whatever. Point is, even though this thing is not charged, and I'm going to say very carefully, in very big letters, not charged, it still has charged parts. This is a bigger idea than you think. So this thing is electrically neutral, which is what we mean when we say not charged. But it still has pieces inside of it that can interact electrically, because it still is built up of pieces that are positively and negatively charged. In a conductor, these are all free to move around. The positives can move, the negatives can move. Stylistically, it works. In an insulator, we had the idea where, it's like the child on one of those kid leashes. The negative charges are kind of bound to the nuclei. They can't get too far away. They're roped into it. And so, when we have this idea, sticking with this idea of a conductor, so if I have, a negative charge swoops in, massive and awe-inspiring, then all of these protons, or all these positive charges, probably not actually protons, because protons aren't going to be terribly movable, they all want to move in this direction. So they start cruising, and they just bump into the wall. And all of them just start piling up over here. Meanwhile, all of the negative charges, the electrons, they're like, oh no, not into this. They start moving here and pile up on the other wall. So we get a buildup of negative charge on this end of the conductor. All these minuses just chilling out on that over there. And we get a buildup of positive charge on this end of the conductor. The conductor still winds up being neutral. We've just kind of shifted where the charge wants to hang out. Now in an insulator we said a similar thing happens, but instead of the charge going globally, so we would say this is maybe global rearrangement of charge. In an insulator we said that this would happen locally. So an insulator, we again have a negative thing over here. We're going to wind up with something that looks like this, where locally all of these things are trying to do the same thing, but they can only do it in a limited small space. And I just made a very cute gesture with my hands that none of you can see. Sorry. This is what we would call a dipole, and it's going to come up a lot in chemistry down the line, so it's a good thing to get into. Dipole, two poles, positive, negative. This is what we would call then a local rearrangement of charge. This is one of the big kind of distinguishing factors here. So, this is a nice picture to have in our mind. It helps us explain kind of some things in terms of how these behave. But in terms of problems, we then had one other thing that we wanted to talk about, and that was this wonderful case where if we have identical conductors, totally identical. And the idea was to kind of play with this idea of charge being able to move freely over a conductor, and also play with the idea of conservation of charge. Conservation of charge telling us, of course, that charge can neither be created nor destroyed, just like we couldn't create or destroy energy. So that means if I start off with 10 coulombs on this, with negative 4 coulombs on this, and this thing is neutral, then my total charge is 6 coulombs. So if I bring all three of these together to touch, and they're not even close to touching actually in that picture. That's close enough to touching. My total charge is still going to be 6 coulombs, but it's now going to be smeared out over this whole thing. So when I separate them, as one wants to do in these problems, I'm now going to find that this 6 coulombs has been spread out evenly over all three. And so that means that there's going to be 2 coulombs on this, 2 coulombs on this, 2 coulombs on this. And so, you know, this one has gained 2 coulombs, this one has gained 6, this one has lost 8. So we can talk about how much charge was transferred off of each of these spheres in terms of what they wind up with. So this is kind of where we're going to start talking about charge. We're not really figuring out like big picture stuff, how much force interacts. We just have that, you know, positive and negative, they attract or they repel, and they can kind of mess with materials. So hopefully this gives you a good starting point, gives you a hand with the homework. Good luck.